The Euclidean algorithm allows us to quickly and efficiently find the greatest common divisor of two integers. An important consequence is known as Bezout's lemma. For any non-zero integers a and b, there exist integers x and y such that a linear combination of a and b gives us the greatest common divisor. There are several ways to prove this, but if we view the Euclidean algorithm to find the greatest common divisor as a process that takes k steps, we can use induction. This time, remember Gauss's dictum, prove it, then prove it again. So let's consider. If a divided by b is some quotient with remainder 0, then the greatest common divisor is just going to be b, and so we have the linear combination 0a plus 1b equal to b. And while we could use this as our base case, let's go ahead and consider the case where we have to do one division with a remainder. So suppose we find the greatest common divisor in one step, so we find our quotient, and this has to be our one step because if we divide by r1, we get q2 with no remainder, and so our greatest common divisor of a and b is r1. And from our first division, we can rearrange this, and here we have a linear combination of a and b that gives us that greatest common divisor, proving the base case. Now assume that Bezout's lemma holds for all pairs of integers where the Euclidean algorithm terminates after k steps. Then suppose the Euclidean algorithm applied to a and b requires k plus 1 steps. So we divide and get a remainder, divide, get a remainder, and so on, and finally we get our k plus first remainder, which gives us an exact quotient and remainder 0. Now, by our induction hypothesis, rk plus 1, the greatest common divisor of b and r1, can be expressed as a linear combination of b and r1. So we know that there's a linear combination that gives us rk plus 1. From our first quotient, we have, and so r1 equals, so replacing r1 with a minus bq1 and doing a little algebra gives us, and we have a linear combination that gives us rk plus 1, and since the greatest common divisor of a and b is rk plus 1, this proves the induction step. So, for example, we can find the greatest common divisor of 119 and 544 as a linear combination of the two numbers. So to do that, let's apply the Euclidean algorithm. And we find our greatest common divisor. Now, since our greatest common divisor is this last remainder 17, let's go ahead and solve all of our equations for their respective remainders. And we find and now we can use substitution. So I do want to get 17 as a linear combination. So I have 17 as a linear combination of 68 and 51. But I know that 51 is 119 minus 1 times 68, and so I can replace and simplify. And now I have 17 as a linear combination of 68 and 119. But I know what 68 is as a linear combination, so I'll replace and simplify. And that gives me 17 as a linear combination of 544 and 119. Now, a useful strategy when learning mathematics, consider the converse. If the greatest common divisor of two numbers is d, then Bezout's lemma tells us that there is some linear combination that gives us d. But what if we have some linear combination that gives us d? Could this be the greatest common divisor? No. If the greatest common divisor is d, then for any constant c, if we multiply everything, we can get a linear combination equal to CD. So we can get any multiple of D as a linear combination. While this seems like we can't get anywhere, remember, you can always change your goals. This does tell us that any multiple of the greatest common divisor can be expressed as a linear combination. In other words, if D is the greatest common divisor, we can find a linear combination of A and B equal to D, 2D, 3D, and so on. Consequently, the least non-negative linear combination of A and B will be the greatest common divisor. Now, in general, this isn't always useful, unless we can find a linear combination equal to 1, which happens with primes and relatively prime numbers. Let's take a look at that. So remember, earlier we proved that if P is prime and P divides a product, then P must divide one of the factors. And back then, we used a descent proof. But remember, try and prove things in more than one way. So suppose P divides AB, but it doesn't divide either number. Since P doesn't divide A, then the greatest common divisor of A and P has to be 1. Consequently, there exist x and y where we have a linear combination equal to 1. Similarly, since P doesn't divide B, there exists an x prime y prime where we have another linear combination equal to 1. Now consider the product of these two expressions on the left. That's going to be 1 times 1, so we can expand. And everything here has a factor of P, so we'll pull that out. And so now I have a linear combination of AB and P equal to 1. And since it's equal to 1, there can be no smaller linear combination. So by what we determined earlier, this must be the greatest common divisor of AB and P. But remember, we assumed that P divided the product, so this is impossible. So it can't be true that P doesn't divide A and P doesn't divide B. P must divide at least one of them. Now at this point it's useful to remember, if you can't find a new proof, try to find new reasoning for an existing proof. So again, let's say we get down to this linear combination, and again we assume that P divided AB, but since the second term also has a factor of P, this means that P must divide 1, which is impossible, leading us to the same place.